In our previous video, we saw that the truth value of a compound proposition is determined by two things. The first one is the truth values of the individual atomic propositions that are used to construct that compound proposition. The second thing is the logic connector that is involved in constructing that compound proposition. When it comes to the logic connectors, it must be remembered that there is a rule associated with each of these logic connectors which governs how the truth value of a compound proposition must vary according to the truth values of the atomic propositions. To depict this, we construct a table called a truth table. So we can construct a truth table in each of these cases of compound propositions. So now we are going to start with negations. Now I told you that there is a rule associated with each of these logic connectors. So what is the rule associated with negations? This is the rule. If P is any atomic proposition, if P is true, if the truth value of P is true, then not P is false. If the truth value of P is true, then the truth value of not P, its negation, is false. If the truth value of P is false, then the truth value of not P is true. This is common sense, right?
Look at this example. Let P be Carl Gauss was a mathematician, which is true, and Q be 17 is an even number, which is false. Because P is true, not P, Carl Gauss was not a mathematician, is false. And because Q is false, not Q, 17 is not an even number, is true.
So we are going to construct the truth table of not P. So we have two columns, one for P, one for not P. We have two rows because P can have two possible truth values. P can be either true or false. Now if P is true according to the rule, not P is going to be false. If P is false, not P is going to be true. This is the truth table of the negation not P. Next, we are going to look at conjunctions. Now, this is the rule associated with conjunctions. P and Q is true only when both P is true and Q is true. This is the rule that is associated with conjunctions. The truth value of P and Q is true only when both P is true and Q is true.
Here is an example of a conjunction. Let P be Putin is a politician. Now we are referring to Vladimir Putin. Of course he is a politician. He is the president of Russia, which is true. And Q be Putin is a humanitarian. Now I am sure you all agree that Putin is not a humanitarian. So the conjunction P and Q, which represents Putin is a politician and a humanitarian, is false.
Now we are going to construct the truth table of P and Q. Now there are 3 columns, one for P, one for Q, one for P and Q. Now, what are the possible arrangements of truth values of P and Q? There are 4 different arrangements, 4 different possible arrangements of truth values of P and Q. The first possibility is both can be true. Second possibility is P can be true, Q can be false. Third possibility is P can be false, Q can be true. Fourth possibility is both can be false. Can you think of any other possible arrangement? I don't think so. So now the rule says P and Q is going to be true only when both P is true and Q is true. Then this is true. This is false. Why? Q is false. This is also false. Why? P is false. This is obviously false. Why? Because both are false. This is the truth table of the conjunction P and Q. Now for the rule associated with disjunctions. Now we are going to consider the disjunction P or Q. P or Q is true when either P is true or Q is true. The truth value of P or Q is true when either P is true or Q is true. Right? Now in conjunctions we saw that P and Q, for P and Q to be true, both P has to be true and Q has to be true. Now here when either P is true or Q is true, P or Q is going to be true.
If we consider the same 2 atomic propositions, P which represents Putin is a politician and Q which represents Putin is a humanitarian, the disjunction P or Q, Putin is a politician or a humanitarian, is true. Why? Though Putin is not a humanitarian, Putin is a politician. So though Q is false, P is true. That is sufficient to make P or Q true.
Okay, let's construct the truth table for this. Again, there's going to be 3 columns, one for P, one for Q, one for P or Q. Okay, so the possible different arrangements of truth values of P and Q are both can be true, P can be true, Q can be false, P can be false, Q can be true, and both can be false. Now, what is the rule associated with disjunctions? P or Q is going to be true when either P is true or Q is true. So here, the first one, both are true, it's going to be true. Here, P is true, Q is false. But the rule says if one of the atomic propositions, if the truth value of one of the atomic propositions is true, that is sufficient to make P or Q true. So this is also true. This is also true. Why? Q is true. Now here both are false, so it is impossible for P or Q to be true. So it got to be false. This is the truth table of the disjunction P or Q. Next we come to unidirectional implications. So we are going to consider if P then Q or P implies Q. Now you already know that P is the antecedent and Q is the consequent. Okay? Now, the rule associated with unidirectional implications is a bit confusing. So, you have to be very careful. The rule says P implies Q is false only when. Here we talk about the only instance where P implies Q is going to be false. P implies Q is false only when P is true and Q is false. This is the rule. Okay? P implies Q is false only when P is true and Q is false. Okay? This is very important. Now, in the first instance, P is true, Q is true, obviously it is true. Now here, the truth value of the antecedent is true, the truth value of the consequent is false, so P implies Q is going to be false. Now when it comes to the third row and the fourth row, things become a bit confusing. Now the rule says P implies Q is false only when P is true and Q is false, but here P is false. So according to the rule, this got to be true, because this says only when P is true and Q is false. Here P is false. This is then, according to the rule, this got to be true. Now in the fourth row, P is false. So according to the rule, this got to be true. Now according to this rule, the truth value of Q is not important when the truth value of P is false. The truth value of the consequent is not important if the truth value of the antecedent is false, right? So these two instances, we say they are true by default. True by default or true by default, or I hope I have spelled it correct, vacuously true, right? These two instances, we say it's true by default or vacuously true.
Here are 4 examples of unidirectional implications. The first one is, if 8 is an even number, then 8 is divisible by 2. Here the antecedent is true and the consequent is also true, which makes the unidirectional implication true. The second one is, if 8 is an even number, then 8 is divisible by 3. Here the antecedent is true but the consequent is false, which makes the unidirectional implication false. The third one is, if 8 is an odd number, then 8 is divisible by 2. Here the antecedent is false but the consequent is true, which makes the unidirectional implication true by default. The fourth example is, if 8 is an odd number, then 8 is divisible by 3. Here the antecedent is false and so is the consequent. This makes the unidirectional implication true by default.
The concept of true by default is something like this. Imagine that the police have apprehended somebody for a crime based on false evidence, and then they present this person to the court. What's going to happen? He's going to win the case with flying colors. Why? Because the evidence is false. the evidence is false, even if he is guilty or not. Because the evidence is false, he will be acquitted. Same way, if P is false, it doesn't matter Q is false or true. P implies Q is going to be true. Then we come to bidirectional implications. Now we know that the bidirectional implication P if and only if Q is actually the conjunction P implies Q and Q implies P. Now we already know the rule associated with these two unidirectional implications. We have to associate that rule with the rule of conjunction. Okay? Now here you know P is true and Q is true. So P implies Q is going to be true and Q implies P is also going to be true. So P if and only if Q is true. Here, if we consider this way, P implies Q, this is going to be false. Okay? Q implies P is going to be vacuously true. Okay? But since this is a conjunction, both ways it must be true. So the overall, the final truth value of P if and only if Q is going to be false. In the third row, this is going to be true by default. P implies Q is going to be true by default. This way, Q implies P is going to be false. Why? Q is true, P is false. So, considering the conjunction, this is going to be false. This is funny. P implies Q is going to be true by default. Why? P is false. What about Q implies P? That is also going to be true because that is also true by default. Why? Q is false, right? So both sides it's true. So since this is a conjunction, this is going to be true. So the only instance where P if and only if Q is going to be true is when both are true or both are false. Again, I repeat, why this is false? Because P implies Q is false, but Q implies P is true. It's a conjunction, right? It's a conjunction. So one is false, one is true, it's going to be false. Here, P implies Q is going to be true, true by default, but Q implies P is going to be false. Okay? When considering the conjunction, it's going to be false. Here, both sides, it's true by default. Why? P is false, Q is also false. So, this is true. Okay? That is the truth table of the bidirectional implication P if and only if Q.
There is a humorous saying in mathematics that may have some truth in it. It goes like this: one is good at mathematics if he knows how to pronounce this name correctly and he knows the true meaning of if and only if. Unfortunately, many students of school-going age do not seem to understand the true meaning of if and only if. For example, you are asked to prove two lines cut by a transversal are parallel if and only if the sum of internal angles on any one side of the transversal is 180 degrees. The image shows two lines AB and CD cut by the transversal EF and alpha and beta, the two internal angles on the right side of the transversal. This is a bidirectional implication. So for the complete proof, you must prove both if AB is parallel to CD, then the sum of alpha and beta is 180 degrees, and if the sum of alpha and beta is 180 degrees, then AB is parallel to CD.
Now we will look at this interesting compound proposition. This can be read as P or Q and not P and Q. It is the conjunction of P or Q and the negation of the conjunction P and Q. So here we are going to construct the truth table. It has 1, 2, 3, 4, 5, 6 columns. 1 for P, 1 for Q, 1 for P or Q, 1 for P and Q, 1 for the negation of P and Q, and the last one is for the conjunction of P or Q and the negation of P and Q. Now the possible different arrangements of truth values are: both can be true, P can be true, Q can be false, P can be false, Q can be true, both can be false. Here P or Q, considering P or Q, this is true, this is true, this is true, this is false. Why? For P or Q to be true, if the truth value of one atomic proposition is true, that is enough for P or Q to be true. Okay, then comes P and Q, then only it is going to be true only in this instance. In all these instances it's going to be false. Why? For P and Q to be true, both got to be true. The truth value of both atomic propositions must be true. Now we have included the truth values of P and Q in each of these 4 different arrangements. What about the negation? Here, since P and Q is going to be true, not P and Q is going to be false. Here it's going to be true. Why? Because this is false. Again here it's going to be true. Why? This is false. Here also it's going to be true. Okay. Now finally we are going to consider the conjunction of this and this. Okay. Since it's a conjunction, this is going to be false. Why? This is true, this is false. Here it's going to be true. Why? This is true, this is true. It's going to be true. Here also it's going to be true. This is true, this is true. Here it's going to be false. Why? P or Q is false. This is the truth table for P or Q and not P and Q. Okay. Now we call this compound proposition exclusive OR. Right? Exclusive OR. P or Q and not P and Q. You will come across this concept when you study naive set theory, and instead of writing it like this, we use a new symbol for exclusive OR. It is something like this. This means exclusive OR, right? Exclusive OR. Okay, this is the symbol. Okay, this is the symbol. So this means P or Q and not P and Q. That's what it means. Okay.
Look at this example. After lunch, you can have only one of the 2 desserts on the table. Here, you are given the free choice to have any of the 2 desserts on the table, but not both. This is what is meant by exclusive OR.
Now, this is the 6th type of compound propositions that we talked about in the 2nd video. In summary, we looked at the truth tables of negations, conjunctions, disjunctions, unidirectional and bidirectional implications, and finally we looked at the concept of exclusive OR, and we constructed the truth table for exclusive OR as well. With that, I am going to stop. Thank you for watching.